So now we are moving to the fourth presentation, which is continues the topic of the additive manufacturing, but it is now we are switching to another material. Now it is bioresorbable polymeric materials, and the presentation will be by Dr. Andy Little, who is also from Loughborough University in the UK.
Hello everyone, I'm Andy Liedl, and yeah, the co-authors have got Silverschmidt, a couple of PhD students, and then the other co-authors are both PhD students. And finally, Wing Ho is our Chinese student that came to us for a couple of months, did most of the experiments. And what I'll be talking about is developing a new tensile testing specimen of 3D printed bioresorbable polymers, particularly looking at the fracture between the 3D printed layers. And this was nothing to do with the presentation, just to get your attention. And I spent most of the day practicing how to pronounce it, which would go Narodny Muzej Serbii. And I actually went there, and it's fantastic. So this is me, my new job. 8 months ago, this was created. My original job started in Leicester as a mechanical engineering student. Moved on to do a PhD then in simulating biodegradable polymers, the mechanical properties, how they're changing over time. Moved on then to Nottingham, where it was more towards manufacturing, so additive manufacturing of tissue engineering scaffolds was primarily what we were working on. And now, a year ago, I got a lecturer position at Loughborough, so I could do whatever I want, because I've chosen to do more mechanics and materials focus to the additive manufacturing side of things. So in this presentation, I'll give you a quick background about some of the stuff that's relevant, go on to our method of producing these parts and what were the results of those, and then hopefully if I have time, some related work. So bioresorbable polymers are used for this kind of plate that will go over a broken bone. The key thing being in a few months or years, the polymer will have been fully absorbed into the body. So as your bone is healing over a period of time, you want the strength of that polymer to degrade at the right time with that, so that as your bone is recovered, you then lose the strength of the polymer. That's the first bit. This is the price of gold from 1970 until 2018. And this is the price of medical polymer that I've been quoted in the last couple of years, so ranging from £20 to almost £200. So a big justification in this work is reducing the amount of polymer that we're using. So making these samples as small as possible, which is also helping with actually getting some good understanding of them. And the process we're using, common MakerBot type printers, automakers, these are also used this same technology as £200,000 bioprinters, where you're basically putting a polymer filament into a melt chamber. It's being molten, being created as a molten pool, which is then extruded out of the nozzle to print. Our example here is a nose with all the space in between, so that cells can go in and grow, and that would eventually turn into cartilage. The thing that we're also interested in is, as you're doing different print settings, that's going to affect your degradation. So if we're coming too far over to this left-hand side, and our strength of that polymer is degrading too quickly, then if the bone isn't fully healed, then that's going to lead to problems. So we need to understand that, which is the other aspect of my work. And then one bit of background information, just the 3D printing process, the steps that you go through. So you start with a 3D model, so it could just be a tensile testing specimen or an anatomical model. And then take it into the software, and it will split it into loads of layers. So the way I think, if you wanted to print this bottle out of toothpaste, you could all think about that and think, right, lots of slices, and then you squeeze your toothpaste in a little layer, similar to this kind of print path, and then next layer squeezing another set of toothpaste on top of that. That's the process that we're doing with the 3D printer to generate the full print path of where the nozzle is going and extruding this material. So then you 3D print the part, you take that's actually producing something called G-code, which is machine code. Print the part and then you test it. The most important thing, as far as I'm concerned, is bond between the layers. So when we print, in the previous presentation, you mentioned mentioning anisotropy. The strength in the vertical direction as you're printing vertically in that print bed is much weaker, potentially half, potentially quarter, and this would only get worse if you've got a carbon fiber reinforced polymer or something like that. So this is by far the weakest aspect of the printed parts, and therefore is the limiting thing we need to improve and further understand. So this is looking in a little more detail at the current way that you generally test. We've got these ASTM type biosamples, are about this big, and then in that narrow gauge section, this is what it looks like after fracture. You can see, as I was describing before, there's filaments that have been laid down. One of the problems is outlined here, the actual bond between those layers is a very strange shape. You've got a small section here, larger section here, this kind of blobby, asymmetric bond at the top. There's no real understanding of how that's generated. You can predict that. You see these ones are wider. We've got a filament coming across here that wasn't supposed to be there, these kind of things. So we want to simplify it to just one filament bonded on top of one filament and just have that single interface. So we have much more control there. We don't have all these polymers going in weird directions and stuff, so the filaments. And with that we get one interface, we can really understand what's going on there. And because of the price of gold and the price of medical grade polymers, we'll be reducing the material a lot because it's just one single interface, one single filament. So this is how we print it. This is actually the parts that we print. You can toss these out like sweeties into the audience. Very good. So we print it like this as a single layer. One filament on top of one filament on one filament. And we end up cutting out our samples on that red sections. So then, normally you want to have that dog bone specimen, right? So you've got the grip sections are stronger and they're not going to fail the grip sections. But we're cutting out rectangles, and the way we're getting that dog bone is by varying our filament width. So this is the representation of the filaments being printed directly on top of one another. We start with wide filaments, come narrower for the gauge, and then wider at the top. This is done not by taking it into 3D printing software and trying to get it to do this, because it wouldn't listen to you, it would do something completely different. We're actually just telling the printer exactly what to do ourselves. We give it these commands as a written text file saying, move the nozzle to here, extrude this much material. And that's been primarily what I've been working on, which is showing scaffolds, is that control. And you can see here the width of those filaments getting wider at that next section. And that's the specimen of them that they've come up with, checking for this work. Okay, somebody told me, tell them what's new, what are you doing that's different from what everyone else does? Obnoxiously telling you all this is first in the world. Not quite that dramatic, but particularly the width of these filaments, varying those to get the dog bone specimen. No, I've never seen anyone do this sort of thing. And the real good thing about that is then we can change the design, instantly reprint a new one. It's not relying on dies being manufactured with different shapes and things. It fails in the next section, the narrowing section, we can change the design just using the strength of 3D printing. So this is validating that we're getting the geometries we're after. The blue line here is showing the width 900 microns in the grip sections, coming down to 600 microns in the narrow section gauge, and then this is the overall width of the filament. Each point is one filament, so there's a lot more filaments than in this picture. And then we also have this bond, so you can see the bond is slightly narrower than the overall width of the filament, so we've measured the bond as well to check. And then interestingly, I think this is probably where it will fail, because it's got the smallest bond, and you only need to fail one point, one single layer is all that will be failing. So it's pretty irregular, so we're not getting some really awful layers with too small ones. And then in terms of the mechanics, the fracture and the strength of these parts, we're getting pretty consistent. There's a few wildcards here, but according to other studies in the literature, they have as much variability or more variability than this, and certain mechanical grooves or repeatability of these. Just through this is the first set of tests we've done for this. And you can see immediately, this is the fracture surface. We've got a full clean fracture. It's very easy to analyze what type of fracture, and to identify the direction where the crack was initiated. Compared to this, it's so much more understandable that we could then tailor specific things, tailor the print speed, tailor the temperature, and it's all the same. At every single point on that specimen I've been handing around, the print nozzle is exactly the same time between layers at every single point, whereas for something like this, it will be up and down, and then it starts here, it's going to be on hot polymer, then cooler, then hot, then cooler, and you're going to have a very complicated bond mixture. Oh, yeah, okay, another one. This is the last one of these, I promise. So that's the fracture surface. The fracture surfaces that we've seen in the literature are much more on this side of things, but to be able to then go and look in detail at that single filament, that's where I really want to take it forwards and start understanding how is it fractured. So before I just go on to the related work, it's basically working. We're using the potential of 3D printing to actually get these structures without having to cut them with particular dyes and change the dyes design. Collaboration, I can do this sort of control of the 3D printers and my students for many different things. So we're doing tissue engineering scaffolds. If you're interested in a different type of test, we'll look at fracture toughness, or if you want to look at fatigue and you need a specific design, then please get in touch and we'll look at whether we can do some custom 3D printing control paths. And yeah, importantly, try and understand 3D printing a lot more. I think there's, at the moment, the understanding of where mechanical properties are coming from 3D printing is not fully based on fully fundamental understanding. So hopefully by isolating that individual filament, that individual interface, we would understand the fullest. So, okay, a couple of minutes. Just an example of a separate advanced control of the 3D printer. Let's say this is a tissue engineering scaffold, and you can see we've got these blocked pores at the top. And the way this was printed, the 3D printer nozzle comes down, moves across, dragging that polymer into that pore, and then moves to the other side, moves across, and it's dragging the polymer and blocks those pores. A super simple change, just coming down and then a little step outside before we move across. Go to the other side, a little step outside, go across. And all that does then is that excess polymer, we can't just switch up and tell it not to print, is being dumped on the outside of our scaffold rather than inside, which was important for this work because they wanted to have consistent pores throughout the whole scaffold rather than inconsistent changes. Then it was similar things for other scaffolds as well. Instead of coming right to the end, cut the corners, and that means you get nice pores on the surface because this was about infiltrating these polymers with hydrogels and cell seeding. And this is what I brought to give you, students. It's an Excel spreadsheet that generates the print code. So you just say, what width do you want these scaffolds to be, what height, what space between the filaments, put all the numbers in here, click the button, and then you've got a 3D printer code that just goes into the printer. And for one specific application, there'll be a new one of these. And that's the thing that normal 3D printing software can't do that, because there are infinite different parameters that you might want to change. And if you try to offer them to everybody, it just the number of parameters that have to work, it wouldn't be possible. And then the final little bit is simulating the extrusion process. So this is simulating a filament being deposited and then another filament going across it. And you can see as it's going across, it's slightly widening because it's being obstructed. And then this is a much larger scaffold structure, just showing that it's a really simple simulation process. It's basically just assuming material is coming out of the nozzle and material can't be deposited where there's already material, so it will have to spread out. That's the simple assumption of this. And with that, we can then get predictions of how the geometry is at the micro scale. So you can see on this one, the filament is getting slightly wider as it's crossing over the previous filaments, and you can see that this is the model results, that's the experimental results. And that's very important for cell seeding when we're talking about the cells actually attaching to 3 filaments and the contact angle between those filaments and stuff, but also for mechanical properties. So this is the 4 different mechanical properties of 4 scaffolds, the compressive modulus. It's this one, which is 4 layers, with filaments being rotated 45 degrees on each layer, and then for the 4 different ones, we reduce the height of that structure so that the filaments will be printed closer together, so there's more overlap, so the actual overlap between the filaments is much wider than in this one, so the mechanical properties are starting, but the compressive modulus is increasing, and the model is able to fit that trend. Whereas without this model, if you just use the CAD kind of representation of that scaffold, you don't get that at all. This is the results of the predicted modulus. That brings me to the end. I don't think